Our plan now is to prove that the 3-SAT problem is NP-complete. What we just saw is that if we have a problem such as SAT, which is known to be NP-complete, then this makes our task much easier. So we're going to use the fact that SAT is NP-complete. This is known as the Cook-Levin theorem. It was proved independently in 1971 by Stephen Cook and Leonid Levin, and they proved that SAT is NP-complete. Now we're going to take this theorem for granted, and later I'll give you some high-level idea of the proof that the SAT problem is NP-complete. Now after Stephen Cook published his paper, then the importance of NP-completeness was highlighted by a paper by Dick Karp in 1972. He showed 21 other problems which were NP-complete. We're going to look at a few of these 21 in the next few lectures. We'll start with 3-SAT, which was one of the 21. Let me give you a quick reminder of the formulation of the 3-SAT problem. So the input to the 3-SAT problem is a Boolean formula f in conjunctive normal form, and we use n for the number of variables and m for the number of clauses in the formula f. Now the extra restriction in 3-SAT as opposed to SAT is that we assume this formula f has the following constraint. Each clause has at most 3 literals. Now the output for the 3-SAT problem is a satisfying assignment if one exists. This is an assignment of true and false to the n variables so that the formula f evaluates to true. Now if there's no satisfying assignment, we simply output no. Now we're going to show now that 3-SAT problem is NP-complete. Before we dive into the proof, let's outline what we need to show in order to establish that the 3-SAT problem is NP-complete. The first thing we need to show is that the 3-SAT problem lies in the class NP. This will be straightforward to prove. Now our main task is to take a known NP-complete problem. In this case, all we know is that SAT is NP-complete. So we have to show a reduction from SAT problem to the 3-SAT problem. Now once we've shown this reduction from SAT to 3-SAT, what does that establish? That establishes that for every problem in NP, we have a reduction from this problem A to SAT, and then we have this reduction from SAT to 3-SAT. Therefore, we have a reduction from A to 3-SAT. The implication of this is that if we have a polynomial time algorithm for 3-SAT, then we have a polynomial time algorithm for every problem in NP, because we can reduce every problem in NP to 3-SAT. So let's start with the easy task. Let's prove that 3-SAT is in the class NP. Now to prove that 3-SAT is in the class NP, we have to show that we can verify solutions efficiently. So let's take a particular input for the 3-SAT problem. So f is our input for the 3-SAT problem. And let's take a proposed solution. So this is a true-false assignment for the n variables. Now we need to check that this assignment is a satisfying assignment for this formula. Now how are we going to verify that this assignment is a satisfying assignment? Well, we're going to go through the clauses. So let's take each clause. For a particular clause C, it'll take us order 1 time to check that at least one of the literals in C is satisfied. Why is it order 1 time? Because each clause has at most 3 literals. Now if every clause C is satisfied, then the formula F is satisfied. It takes order 1 time per clause. There's M clauses, so it takes order M total time to verify that this assignment satisfies the formula. So this proves that the 3-SAT problem is in the class NP. Now let's look at the task of reducing SAT to 3-SAT. Let's outline first what we need to prove. Now we're assuming we have an algorithm, a polynomial time algorithm for the 3-SAT problem, and we're going to use this as a black box. And we're going to construct an algorithm for the SAT problem using this 3-SAT algorithm as a subroutine. So what do we need to do? We need to take an input for the SAT problem. So we have an F, which is an input formula for the SAT problem. Then we have to transform this input f into an input for the 3-SAT problem. We'll use f prime to denote the input to the 3-SAT problem. Now this is a bit tricky to do. Why? Because f might have some big clauses. It might have some clauses which contain maybe n literals. But our input for 3-SAT has to have clauses of size at most 3. So somehow we have to transform these big clauses into a series of small clauses. And we need to do it in such a way that if we have a satisfying assignment sigma prime, which is a satisfying assignment for f prime, our 3-SAT formula, then we can transform this satisfying assignment for the 3-SAT input into a satisfying assignment sigma for the original SAT input. Moreover, we want that if our 3-SAT formula f prime has no satisfying assignment, so there's no sigma prime, so the algorithm is going to output no, we want that our original SAT formula f also has no satisfying assignment. So we want that f prime has no satisfying assignment if and only if f has no satisfying assignment. In that way, we can simply output no in both cases. So once again, what do we need to do? We need to take an input f for the SAT problem, and we need to create an input for the 3-SAT problem. And then, given a satisfying assignment sigma prime for the 3-SAT input, we need to transform it and make a satisfying assignment for the SAT formula. And we need that sigma prime satisfies f prime. So this is a satisfying assignment for f prime, the 3-SAT input, if and only if this transformed output, sigma, is a satisfying assignment for our original SAT formula. So we have a satisfying assignment for the 3-SAT input if and only if we have a satisfying assignment for the SAT formula. Why do we need this equivalence? Because we need that no instances for the 3-SAT formula correspond to no instances for the SAT formula. So if we get a no output, we can output a no for the SAT input. Now this is the main task, so let's dive into it. We want to take an input f for the SAT problem and transform it into a valid input for the 3-SAT problem. Now let's try to get some idea for the reduction. So let's take a sample input for the SAT problem. So here's a formula with 4 variables and 3 clauses. Let's label the clauses as C1, C2, and C3. Now let's define our input for the 3-SAT problem. Let's denote this as f prime. Well, clause 1 and clause 3 we can keep the same. Those are valid inputs. Those are valid clauses for 3-SAT. Now the challenge is, what do we do with the second clause? This is a clause of size 4, but valid inputs for 3-SAT have size at most 3. So what are we going to do for this second clause? Well, we're going to create a new variable y. And we're going to replace this second clause by the following pair of clauses. So it's x2 bar or x3 or y. These are the first 2 literals in C2. And the second clause is y bar or x1 bar or x4 bar. These are the last 2 literals in the clause C2. Now the key claim is that this original clause C2 of size 4 is satisfiable if and only if this new pair of clauses is satisfiable. So C2 is satisfiable if and only if C2 prime is satisfiable. Therefore, replacing C2 by this pair of clauses makes an equivalent formula. And in this new formula, all the clauses have size at most 3. Now let's go ahead and prove this claim so that we have some idea how to generalize this construction. So here's our original clause of size 4. And here's our new pair of clauses, each of size at most 3. And we want to prove that this original clause C2 is satisfiable if and only if this new pair of clauses C2 prime is satisfiable. Let's do the forward direction first. So let's take a satisfying assignment for C2. This is an assignment for x2, x3, x1, and x4, which satisfies this clause. And we want to show that there is a satisfying assignment for C2 prime. Now, in order for this assignment to satisfy C2, one of the 4 cases must hold. Either x2 equals false, x3 equals true, x1 equals false, or x4 equals false. Maybe some combination of those hold, but at least one of those has to hold. We'll break up these 4 cases into the following pair of cases. We'll consider whether x2 equals false or x3 equals true. These are the pair of literals which appear in the first clause of C2 prime. And the other case is if x1 equals false or x4 equals false. This is the pair of literals which appear in the second clause of C2 prime. Now if x2 equals false or x3 equals true, then we're going to set y to be false. Notice in this case we have x2 is false or x3 is true. Therefore the first clause is satisfied. And we're setting y to be false, so this satisfies the second clause. So C2 prime is satisfied in this case. Similarly, in the second case, if x1 is false or x4 is false, then we set y to be true. In this case, since y is true, this satisfies the first clause, and since x1 is false or x4 is false, this satisfies the second clause. And given a satisfying assignment for C2, we've constructed a satisfying assignment for C2 prime. Now let's look at the reverse implication. In this case, we're going to take a satisfying assignment for C2 prime, and we're going to construct a satisfying assignment for C2. What we're going to show is that if we just ignore y, whatever the assignment was for x1, x2, x3, and x4, which satisfied C2 prime, that's going to satisfy C2. Now there will be 2 cases. Either y is true or y is false. Suppose y is true. We know that C2 prime is satisfied. So each of these 2 clauses is satisfied. Y is true, so that satisfies this clause. How about this second clause? Well, either x1 must be false or x4 must be false. Well, if x1 is false or x4 is false, both of these satisfy C2. So in either of these scenarios, we have an assignment which satisfies C2. Now suppose y is false. So this assignment for y satisfies this second clause. How do we satisfy this first clause? Well, we're assuming that this is a satisfying assignment for C2 prime. So it must satisfy this first clause. Y is false, so that's not helping. So it must be the case that either x2 is false or x3 is true. So either x2 is false or x3 is true. Now if x2 is false, that means that this is an assignment which satisfies C2. And if x3 is true, then also this is an assignment which satisfies C2. So in any of these four cases, we have an assignment which satisfies C2. So every satisfying assignment for C2 prime, if we ignore y, it's also a satisfying assignment for C2. And this establishes the reverse implication. We've done both directions, so we've shown the if and only if. Now we just saw how to transform a clause of size 4 into a pair of clauses of size 3. Now let's try to generalize this idea. Let's do it one step at a time. So let's take a clause of size 5 now, and let's try to transform this into a pair, or actually a triple of clauses of size 3. Now previously, to transform the clause of size 4 into a pair of clauses of size 3, we added one new variable y. Now to transform a clause of size 5 into a triple of clauses of size 3, we're going to create two new variables, y and z. Now we're going to make a formula C prime, which is 3 clauses, and each of these clauses is going to be of size at most 3. Actually, they're going to be of size equal to 3. And we want to do this in such a way that C is satisfiable. The original clause C is satisfiable, if and only if this triple of clauses, C prime, is satisfiable. And therefore, in our original input f, if we have a clause such as this, we can replace it by this triple of clauses and we'll get an equivalent formula. Now the quiz is to define C prime. To find this triple of clauses, each is of size exactly 3 literals, and use this pair of new variables, y and z. For simplicity, for entering your solution, let me enter the OR symbols for you. And also to simplify your input, let's relabel these literals. So let's relabel these 5 literals as A, B, C, D, E. So A is equal to x2 bar, B is equal to x3, C is equal to x1 bar, D is equal to x4 bar, E is equal to x5. So use A, B, C, D, E, and Y and Z, and create a formula, C prime, such that C prime is satisfiable if and only if C is satisfiable. The solution is the following. I take the first 2 literals, x2 bar or x3, or y, the new variable. That's the first clause. The second clause is the following. I take y bar or x1 bar, the third literal, or z. The last clause is z bar or x4 bar, the fourth literal, or x5, the fifth literal. Instead of formally proving this now, let me give you a quick idea of the proof, and then we'll do the general construction, and then we'll prove the general construction is correct. Let's suppose that we have a satisfying assignment for C, and let's see how we construct a satisfying assignment for C prime. So one of these 5 literals must be satisfied. Let's suppose the middle one, x1 bar, is satisfied, so x1 is set to false. So that's going to satisfy this second clause. How do we satisfy the first and third clause? Well, here we use these auxiliary variables. Setting y to true satisfies the first clause, and setting z to false satisfies the last clause. And in general, one of these 5 is going to be satisfied. That's going to satisfy one of these 3 clauses, and then we can use these other 2 auxiliary variables to satisfy the other 2 clauses. How about the reverse implication? Suppose we have a satisfying assignment for C prime. How do we get a satisfying assignment for C? Well, take the case where y is false. So this literal is not satisfied, so one of these 2 literals must be satisfied. If one of these 2 literals is satisfied, they're satisfied here as well, so C is satisfied. Now suppose that z is set to true. Then this literal, z bar, is not satisfied, so one of these 2 literals must be satisfied. Either x4 is set to false or x5 is set to true, in which case one of these last 2 literals of C is satisfied. The last case is the complement of these 2. Y is set to true and Z is set to false. Well, since we're taking a satisfying assignment for C prime, look at how this second clause can be satisfied. Y is set to true, and z is set to false, so these two literals are not satisfied. So the only way to satisfy this clause is to set x1 to false. So if x1 is set to false, then we satisfy this third literal in C. Now let's do the general construction. Let's say we have a clause of size k. Now we're going to create a series of clauses, which is equivalent to this original clause. Now when we had a clause of size 4, we added one new variable and we had a pair of clauses. When we had a clause of size 5, we created two new variables, and then we had a triple of clauses. Now if we have a clause of size k, we're going to create k minus 3 new variables, and we're going to create k minus 2 clauses. So let's go ahead and do the general construction now. Let's consider now a general clause of size k, and let's label the literals in this clause by a1, a2, up through ak. Now for this clause, we're going to create k minus 3 new variables. Recall that when k was 4, we created one new variable. When k was 5, we created two new variables. In general, we're going to create k minus 3 new variables. Let's label these new variables as y1 through yk minus 3. Now it's important to note that every clause of size greater than 3 creates new variables. And these new variables are distinct for each clause. So for each clause, we might create order n new variables. There's m clauses, so we might have order n times m new variables in total. Now we're going to replace this original clause c by the following k minus 2 clauses. So we take the first two literals, a1, a2, and the first new variable, y1. And the first clause is a1 or a2 or y1. Then we use the negative of the first new variable, the third literal, a3, and then the positive of the next new variable. And this gives us our pattern. So we then use y2 bar, the negative of the second variable, and then we use the next literal, a4, and then we use the next new variable, positive form, y3. Now we continue this pattern, and then the last two clauses look as follows. So the penultimate clause looks as follows. It's going to have yk minus 4 bar, or ak minus 2, this is the third to last literal, or yk minus 3, this is the last new variable in the positive form. So this penultimate clause follows the same pattern. The last clause is going to be slightly different. It has yk minus 3 bar, same pattern as before. And then we use the last two literals of C. So we have ak minus 1 or ak. This defines our formula C prime. Now our claim is that the original clause C is satisfiable if and only if this new sequence of clauses C prime is satisfiable. Now for our original input to the SAT problem, for every clause which is size bigger than 3, we can replace it under this following construction. We take this clause which is size bigger than 3, we replace it by this sequence of clauses which are all of size exactly equal to 3, and then we get a valid input to the 3-SAT formula. And the key is that this new formula is satisfiable if and only if the original formula is satisfiable. We get an equivalent formula. So let's go ahead and prove this claim that C is satisfiable if and only if C prime is satisfiable, and then we'll be pretty much done with the reduction. Now this was our construction. We took this clause of size k. So we took C, which was a1 or a2 up to ak, and we defined this formula C prime, which consisted of k minus 2 clauses. And our claim is that C is satisfiable if and only if C prime is satisfiable. Now let's prove this claim. Let's start with the forward implication. So let's take an assignment to these literals which satisfies this clause C. And let's prove that there's a satisfying assignment to C prime. Now in order for this assignment to satisfy C, one of these literals must be satisfied. Let's let AI be the first satisfied literal. So let AI be the first literal satisfied. Now if AI is satisfied, that's going to satisfy one of these clauses. If I equals 1, so A1, that's in the first clause. And if I is at least 2, then AI appears in the I minus first clause. So this literal AI being set to true satisfies the I minus first clause of C prime. Let's suppose I equals 4. So we have A4 equals to true. And this clause is satisfied, so we can remove it. Now, what about the I minus 2 earlier clauses? Well, we can use these positive forms of these auxiliary variables to satisfy these earlier clauses. So we set y1 and y2 to be true in this case, and in general we set y1 through yi minus 2 to true, and this satisfies the first I minus 2 clauses of C prime. So this setting of the first I minus 2 auxiliary variables satisfies the first I minus 2 clauses. AI set to true satisfies the I minus first clause. What do we do about the later clauses? Well, here we're going to use the negative form of these auxiliary variables. We set the remaining auxiliary variables to false. In this case, yk minus 4 bar and yk minus 3 bar. And in general, we set yi minus 1 through yk minus 2 to false, and this satisfies the remaining clauses which appear after the I minus first clause. The punchline is that this literal satisfies the I minus first clause of C prime. We use these auxiliary variables to satisfy the earlier clauses, and we use these auxiliary variables to satisfy the later clauses. So we only need one literal of C to be satisfied, and then we can use the auxiliary variables to satisfy all the other clauses of C prime. Now let's do the reverse implication. Now let's prove the reverse implication. So let's take an assignment to these original K literals and these auxiliary K minus 3 variables, which satisfy C prime, and let's prove that there's a satisfying assignment for C. What we'll do is we'll just ignore these auxiliary variables, and we'll prove that these settings for these original K literals satisfies the original clause. Now, in order to satisfy this clause C, we just need to show that at least one of these literals is set to true. Let's suppose that's not the case. Suppose all of these K literals are set to false. Under this assumption, is it possible to satisfy C prime? We'll show it's not possible. Now we're supposing we have an assignment which satisfies C prime, so it satisfies all of these clauses. Let's look at the first clause. Now we're supposing that A1 and A2 are set to false, so these first two literals are not satisfied, so the third literal must be satisfied. That means Y1 must be set to true. That's the only way to satisfy this clause under this assumption. Similarly, let's look at the second clause. Well, we're saying Y1 is true, so this literal is not satisfied. Also, A3 we're assuming is set to false, so this literal is not satisfied, so we better satisfy this third literal, Y2. So Y2 has to be set to true. Continuing it on, look at the penultimate clause. In order to satisfy this penultimate clause, we have to satisfy this literal. So we have to set yk minus 3 to be true. Now look at the last clause. Well, yk minus 3 is set to true, so this literal is not satisfied. Similarly, these last two literals are not satisfied because they're set to false. So this clause is not satisfied. That means that C prime is not satisfied. That's a contradiction. We were assuming that this was an assignment which satisfied C prime. So that means that this assumption that all of these literals are set to false is not true. So at least one of them must be set to true, and therefore that literal satisfies this clause C. So if we just ignore the assignment to these auxiliary variables, then the setting for the original literals satisfies this original clause C. Now we can formalize our reduction from SAT to 3-SAT. So let's consider an input formula for the satisfiability problem. And let's create an input formula for the 3-SAT problem by the following procedure. Let's consider the clauses of F one by one. So for clause C in F, we'll have two cases, depending on whether the clause is of size at most 3 or strictly bigger than 3. If C contains at most 3 literals, then we can add this clause as is to this new formula. Now what if C contains more than 3 literals? Then we have to use our previous construction. In this case, we create k minus 3 new variables, as we said before, and we replace C by this new formula C prime, this sequence of k minus 2 clauses, as we defined before. So, small clauses stay the same, big clauses are replaced by k minus 2 new clauses, as we defined before. Now that we've defined the input to the 3-SAT problem, now we have to prove that this original input to the SAT problem is satisfiable. F is satisfiable if and only if this input to the 3-SAT formula, F prime, is satisfiable. So F is satisfiable if and only if F prime is satisfiable. Now this statement is quite straightforward to prove, given that we've already proven that C is satisfiable if and only if C prime is satisfiable. Then afterwards, the remaining task is to show that given a satisfying assignment to F prime, we can construct a satisfying assignment to F. That again will be straightforward because we just ignore these auxiliary variables, and the setting for the original variables will give us a satisfying assignment to the original formula. Let's prove this equivalence, and hopefully it seems obvious given what we've shown so far. So let's start with the forward implication. So let's take an assignment to the original n variables which satisfies the original formula f. Now we want to show that keeping this assignment the same for these original n variables, there is an assignment to the new variables so that this new formula f prime is satisfied. Now since we're keeping the assignment for these n variables the same, and the new variables are distinct for each new clause, therefore we can look at it clause by clause. So let's look at clause C in the original formula f. If C has at most 3 literals, then it's obvious. If C is bigger than size 3, then we replace C by this sequence of k-2 clauses called C prime. Now the key is that C prime uses k-3 new variables. These variables only appear in C prime for C. They don't appear in any other sequence of clauses. So the new variables for C are distinct from the new variables for any other clause. So we can set these variables however we want with respect to C, and this won't affect any other clauses. And what we saw before is that there is an assignment to these k-3 new variables so that this new formula C prime is satisfied. In particular, we took the first literal satisfied in C, call it AI, and then we set the first I-2 new variables to true, and the remaining new variables to false, and we showed that that satisfied C prime. Now let's look at the reverse implication. Let's take a satisfying assignment for f prime, and we want to ignore the assignment for the new variables and show that the assignment for the original n variables satisfies f. Consider a sequence of clauses corresponding to some C prime in f. What we saw before is that at least one of the literals in the original clause C must be satisfied. If all of these literals in the original clause were set to false, then there would be no way to satisfy this clause, sequence of clauses C prime. So therefore we can ignore the setting on the new variables, and just looking at the setting on the original n variables, that's going to satisfy each of the clauses in the original formula f. Now going back to our earlier reduction, we showed how to take an input formula for SAT and transform it into an input formula for 3-SAT. This was the reduction for creating f prime, and then we just proved that the original formula f is satisfiable if and only if this new formula f prime is satisfiable. Now what remains? Well, we run our 3-SAT algorithm, our black box algorithm, on f prime. If it produces no, that there's no satisfying assignment, then we say no, there's no satisfying assignment for f. What if it produces a satisfying assignment? So suppose it gives us this satisfying assignment sigma prime, which satisfies f prime. Well, we have to produce a satisfying assignment for f. How do we transform this satisfying assignment sigma prime to a satisfying assignment for f? Well, what we just saw from this proof is that if we ignore the assignment for the new variables and keep the assignment for the original variables the same, then we get a satisfying assignment for f. So we take this satisfying assignment for f prime, we ignore the assignment for all of the new variables, and the assignment for the original variables gives us a satisfying assignment for f. And that completes our reduction. One last thing to note is what is the size of f prime? F, our original input to SAT, has n variables and m clauses. How many variables does f prime have in the worst case? Well, we might create n new variables for each clause. So it has order nm variables in the worst case. And we're also replacing every clause by order n clauses in the worst case. So we have order nm clauses. But this is okay because the size of f prime is polynomial in the size of f. So if we have an algorithm which is polynomial running time in the size of f prime, it's still polynomial in the size of f as well. So this completes our first NP completeness proof. Now that you've seen your first NP completeness proof, the fact that 3-SAT is NP complete, there are a few relevant practice problems from the textbook that you can try now. In problem 8.3, they consider a variant of SAT called stingy SAT, and you want to prove that stingy SAT is NP complete. In problem 8.8, you consider exact 4-SAT. This means that every clause has exactly 4 literals, not at most 4 literals, but exactly 4 literals in every clause. And you want to prove that exact 4-SAT is NP complete.